Hey everybody, I'm Seth. I'm here with Reagan and Zach, and today we're going to talk about our hot air balloon controller project, which we did for this class. But before we get too far into our presentation, we want to give a special thanks to Dr. Hedegren, Dr. Thomas A. Badgewell, and also our classmates. The objective of this project was to design a PID controller that uses two actuators to control the elevation of a hot air balloon. We feel that through all of the experiences we've had in this course and all that we've learned, that we are proficient and expert in dynamic system analysis, parameter regression, controller design, and controller tuning. We really feel that this is kind of an extended case study homework, much like we've done a lot through our classwork. And the objective of this presentation ultimately is to show you all what we did to design this controller and how we did it.
So the fundamental basis behind our controller is the physics-based model that was provided to us by Dr. Badgewell. It uses a standard model of the atmosphere, and the balloon runs on two fundamental balances, one being the vertical force balance that takes into account lift, gravity, and the drag force acting on the balloon, as well as an energy balance acting on the hot air balloon gases, where we have convection with the atmosphere, as well as heat addition through the combustion of the fuel gas, as well as hot gases leaving through the vent, which pulls energy out of the balloon.
Our system is comprised of two actuators, a fuel gas valve, which releases fuel into a small heater or burner that produces hot air or hot gas, and then a vent valve at the top of our balloon that releases that gas, essentially ideally lowering your balloon's elevation. A sensor for the system would be an elevation sensor, and we set up our controller using a series of desired set points, elevation set points. Other variables we were interested in and wanted to observe were our balloon velocity, the velocity of its altitude change, so in meters per second, how quickly it rises or lowers, and the balloon gas temperature.
So in order to do this, we first started by doing a series of step tests or doublet tests to have some data to fit an FOPDT to, which is a first order plus dead time model. I ran an FOPDT and I also decided to run an SOPDT, which is a second order plus dead time model, just to see which would fit better. We ultimately decided that the FOPDT would fit our data and in this situation better, so that's what we went with. We then regressed parameters for both of the actuators, being both the fuel gas valve and the balloon vent valve, to be able to use those both well.
We were very curious on how to make the best PID controller for the balloon, so we developed them for three different scenarios. The first scenario was using both actuators freely, so the fuel valve and the vent valve. The second scenario was using the fuel valve freely and only initializing the vent valve when our velocity was greater than 2 meters per second. The third scenario was only using the fuel valve freely and never using the vent valve as a way to change our altitude.
In order to quantifiably compare these different controllers, we put all of them up against the same set point test that they had to follow. Here is an example of one of the PID tuning simulation or PID controller simulations. We took the FOPDT parameters that we received from the regression, put them into IMC tuning correlations, and then further tuned those parameters to decrease the integral absolute error to develop the best performing controller.
Here's a animated GIF of our results. As you can see, they all followed and behaved pretty similarly. They were able to follow the set points. We were pleased with how they followed the set points. Scenario A, which was using both actuators freely, is in green. Scenario B, which is using the fuel gas actuator freely and the vent valve based on velocity, is in the blue. And the red is using only the fuel gas valve. They all behaved very similarly and had similar oscillatory behavior that wouldn't be negative or harmful to our actuators. This is a stagnant graph of all three combined, and it includes the integral absolute error for each of the three. We found that scenario A, using both actuators freely, gave us the least error.
So ultimately, we determined that the PID controller that uses both actuators freely was the best result for this because it matches the set point changes best, which is shown by the lowest sum of absolute errors, but it also has minimal oscillatory behaviors.
Moving forward, we would want to test this on a small scale balloon to prove its validity, and then implement our controller in a full-size hot air balloon or other applications similar to it. Thank you.